അമൃതമാകണേ അമ്മ നൽകുമമ്മ പോലും അമൃതമാകണേ പൂനമീ ചരാചരങ്ങൾ ഗുരുവരങ്ങളാകണേ ഹൃദയരാഗതന്ത്രി മീട്ടി സ്നേഹഗീതമേകിയും കർമ്മഭൂമി തളിരിടുന്ന വർണ്ണമേകിയും നമ്മെ വാഴുമാദിനാമം ഇന്ന് വാഴ്ത്തിടാം.
Thank you, Mabel. Now, I would like to call upon the pillar of this program, a very energetic person, our head of the department, Ms. Smita Davies, to introduce about the speaker.
Good evening, all. It's my pride and privilege to introduce the speaker for the day, Sri Albert Antony, Assistant Professor, Panampally Memorial Government College, Chalakudy. One of the most passionate academicians in mathematics I have ever came across. A man who has thorough knowledge in almost all branches of mathematics. Students always consider that they are lucky enough to hear his class. Actually, I'm also a student of him since I love hearing his classes he posts in YouTube channels. Actually, the pandemic situation has some benefits too. A man who has loved mathematics before anything, not for fame, not for number of research publications or anything. He just loved mathematics purely, as pure the subject is. Though I should mention he has research publications to his credit, which he has done out of his passion. I welcome you, sir, wholeheartedly to interact with the young enthusiastic learners in mathematics. Welcome, Albert, sir.
Okay, thank you, Smita.
Thank you, Smita, ma'am. I'm heartfully welcome you, ma'am, for this program. With great honor and respect, may I invite our chief guest, Albert Antony, sir, Assistant Professor, Panampally Government College, Chalakudy, to speak about the topic, Applications of Density Theorem. It's my pleasure, sir, to welcome you for this National Enrichment Program. Sir, please.
Okay, thank you, Amrita. First of all, I extend my sincere gratitude to the Department of Mathematics of SHC College, Chalakudy for giving me an opportunity in this program. I wish all the very success to the whole mathematics team of SHC College, Chalakudy. Before we start, I would like to mention few things. The first one is, I am a great fan of blackboard and white chalk. I always think something is missing in every online mode classes. But this is a COVID situation, we have no other option. So I also admit the same. The second one is the heterogeneous nature of the audience. I think both the UG and PG students are the participants of this session. So my challenge is to find a suitable equilibrium point for the both. The third one, I have a request. Dear students, please be ready with the notebook and a pen for this session. Shall I present the topic?
Yes, sir, please.
Vijita ma'am, is it audible and visible?
Yes, sir.
Okay, thank you. So myself is Albert Antony, Assistant Professor of Mathematics, from PM Government College, Chalakudy. My email ID is albertanit@gmail.com. In fact, this is the storyboard of today's session. There are 5 questions in the screen. Does there exist a function f from R to R which is discontinuous everywhere? This is the first question. Just for a moment, you please admit that such a function will exist. Then can you imagine the graph of such a function? Okay. The second question is, before introducing the second question, when we loosely speaking about continuity, we will say if a function f is continuous at x equal to a, then left hand limit equal to functional value equal to right hand limit. So maybe our first thought regarding continuity is that if a function f is continuous at some point a, then it must be continuous at least on some small interval containing a. The question is whether this thought is right or wrong. If there exists such a function, you just imagine the graph of such a function. That is, we have to draw a function which is discontinuous everywhere other than at a single point. I think you got the question. The third question is, there is no much difference between the question 2 and question 3 because only the word continuity is replaced by differentiability. But I think that's a nice discussion. The fourth question is, that is a very easy question. Does there exist a non-Riemann integrable function on 0, 1? I think we all are very much familiar with the famous non-Riemann integrable function, that is Dirichlet's unit function. F of x equal to 1 if x is rational, 0 if x is rational. So I am changing my question. So my question is, give an example other than this one. Don't say the case of 1 is replaced by 2 or 1 is replaced by 3, something like that. That is f of x equal to 2 if x is rational, 0 if x is irrational. That are all dependent solutions. We need independent solutions. Okay, that is the fourth question. Then now we are moving to the fifth question. Okay, read the fifth question carefully. If we have at least one solution for the questions 1 to 4, then automatically we can generate infinitely many solutions for all cases or 1 to 4 cases. That is, for example, consider the first question. That is, if we have an everywhere discontinuous function, then automatically we will have infinitely many such functions. The purpose of today's session is the generation of such functions within 5 seconds at the most. Okay, that is the main purpose of today's session. That is, we have to answer question 5 within 0 time. Okay, this is a challenge, and I think we are ready to accept the challenge. Okay, now we are moving to the title of the session, density theorem. I think you are very familiar with the concept. For the we are very familiar with the density theorem. What is the actual definition? Actual definition is this one: if x and y are any two real numbers with x less than y, then there exists a rational number R such that x less than r less than y. That is, between any two real number, we will have a rational number. Okay. Then my question is, what about x less than r? We have another rational between x and r, call it as r1. Therefore, automatically, we will have two rationals between x and y. Continuing in this manner, we will have infinitely many rationals between any two real numbers x and y. So, the theorem says that there exists at least, but the actual thing is we will have infinitely many rational between any two real numbers. This is why we technically call Q is rationals are dense in R. That's why density theorem. Rationals are dense in a huge amount of rationals between any two real numbers. The same is true even in case of irrationals also. That is, if x and y any real numbers with x less than y, then there exists an irrational number I such that x less than y. In fact, it is not there exists an irrational number. In fact, there are infinitely many irrationals between any two real numbers. So irrationals are also dense in R. So R has a dense subset. That the first one is Q. Whose complement? What is that? R minus Q. That is also dense in R. That is, R has two dense subsets. Their intersection is empty. That is the crux of, that is the very important thing that included in this density theorem. That is, both rationals and irrationals are dense in R, but their intersection is empty. That is very important. Okay, this idea that will help us to generate all such functions as answers for the first slide. Okay. The next one is sequential form of density theorem. Before going to that, I have to mention certain things. I feel a mathematical analysis student always tries to get the sequential criteria for almost all concepts in analysis. For example, you just imagine the definition of continuity. After defining continuity, you formulated sequential criteria of continuity, and then we explored sequential criteria of continuity rather than the actual definition of continuity. The same happened in case of uniform convergence also. That is, we explored the sequential criteria of uniform convergence rather than the actual definition of uniform convergence. In a similar manner, we are trying to explore the sequential form of density theorem rather than density theorem. Okay, we have density theorem, we admit that, but we are concentrating much more on sequential form of density theorem rather than the actual form of density theorem. So what is that? Sequential form. The statement is this one: if x is a real number, then there exists a sequence of rational that converges to x. Similarly, if x is a real number, then there exists a sequence of irrationals that converges to small x. That is, if any real number x is given to you, we can construct a sequence of rationals or irrational that converges to that small x. The proof is not hard. This is a very simple proof, in fact. Actually, theoretically, in a theoretical way, the proof is very simple. But in a practical way, the construction of such sequences in a practical way, that is not so easy. For example, this is the proof. Let x be any real number. Then for each natural number n, x minus 1 by n less than x plus 1 by n, definitely. So now we are in a position to apply density theorem, because we have two real numbers less than, one is less than the other, but what is that? X minus 1 by n less than x plus 1 by n. Therefore, by density theorem, n is a variable. Therefore, there exists a rational number R1 between x minus 1 and x plus 1. There exists a rational number R2 between x minus 1 by 2 and x plus 1 by 2, and so and so. So generally, x minus 1 by n, x plus 1 by n, there exists a rational number Rn, such that x minus 1 by n less than Rn less than x plus 1 by n. Because the density theorem will guarantee the existence of such Rn. But you just consider x minus 1 by n. What is limit of x minus 1 by n? 1 by n tends to 0. Therefore, limit x minus 1 by n, that is equal to 0. That is equal to 0. What is limit of x plus 1 by n? That is again 0. No, by this inequality, Rn is the sandwich of x minus 1 by n and x plus 1 by n, and both are converges to the same value. Therefore, the sandwich R by n also converges to the same value x. Therefore, if you take any arbitrary real number x, we can construct a sequence of rational numbers Rn so that limit Rn equal to x. Okay, the same thing. We can prove the very same thing for the irrational case also. So that means if an irrational number is given to you, we can construct a sequence of rationals that converges to that irrational number, or vice versa. This is the theoretical proof is so easy, but in a practical way, such constructions are not so. This is one of the nice example for such a construction for the. Okay, this is a famous example in Robert Bartle's. 1 minute. Okay, this is a famous example in Robert G. Bartle's books. I think in Bartle's book, 2 is replaced by a, and the observations are sequence xn is monotonically decreasing and bounded below and converges to root a. Here a is replaced by 2, therefore this sequence is converges to root 2, the famous Mesopotamian formula. So if you set x1 equal to 1, or you just think that for a moment assume that xn is rational, then 1 by xn is rational, 2 by xn is rational, then rational plus rational is rational, half of rational is rational, then xn plus 1 is rational. That is, if xn is rational, then xn plus 1 is rational. Therefore, if we set x1 equal to 1, automatically x2 is rational, x3 is rational, and so and so, but xn converges to root 2. So this is a nice example of the construction of sequence of rationals that converges to any rational number. Similarly, if we have a rational number, we can construct a sequence of the rational that converges to that value. That is the almost similar difficulty. Okay. So you please be aware of the sequential form of density theorem. This is one of the examples. Now, next, I already mentioned this one, sequential criteria for continuity. The version is this one. A function f from R to R is continuous at a point A in R. If for every sequence xn in R that converges to A, the sequence f of xn converges to f of A. Right? That is xn converges to A implies you take f on both sides. F of xn converges to f of A provided f is continuous at x equal to A. I am repeating, xn converges to A implies apply f on both sides, then f of xn converges to f of A, right? If the condition is f is continuous at x equal to A. Okay, then I think now we are in a position to answer one question. Please, students, please try this question. Show that limit cos 1 by n equal to 0. Show that limit cos 1 by n equal to show that limit cos 1 by n equal to 1 as an application of sequential criteria of continuity. I am inviting all the students to write the answer. The question is this one: show that limit cos 1 by n equal to 1. Please try this problem as an application of sequential criteria of continuity. This is the question. I think you completed. Okay. So we are moving to the next one. Now we are trying to answer all the fifth questions in the first slide. The first one is the construction of a everywhere discontinuous function. Okay, that we are f from R to R. We have to find out a function. That must be a function. At the very same time, it must be discontinuous everywhere. To plot such functions are not so easy. So here look at the function. The function is f of x equal to 1 if x is rational and minus 1 if x is irrational. We already mentioned that q is rational, q is dense in R, irrational. R minus q is dense in R, but their intersection is empty. So this function, if it keeps the rational path, then that will goes to 1. If it keeps the irrational path, then that will goes to the value minus 1. So this is not the exact way of expressing this function because rationals and irrationals are dense. So 0 is rational, therefore its value is 1. 1.1. What is that 1? But between at 0.1 its value is 1. But between 0 and 0.1 there are infinitely many rationals, therefore it will take the value minus 1 infinitely many times. It will take the value minus 1. Similarly, between 0 and 0.1 there are infinitely many rationals, therefore this function will take the value 1 infinitely many times. So we are similarly discuss or you just think about the value of this function at all points of R. So our claim is this function is, look at the values 1 and minus 1. Our claim is this function is discontinuous everywhere on A. The proof is like this. The proof is very simple. Assume the contrary that f is continuous at x equal to A. Some point. At some point f is continuous, that point is a rational point. So our contradictory assumption is this one: f is continuous at x equal to A, where A is an irrational point, where A is any rational point. So by the sequential form of density theorem, there exists a sequence of irrationals in such that in converges to A. This is nothing but the sequential form of density theorem. So no doubt we can think about a sequence of irrational that converges to A, where A is a rational point. What is a function? At the rational points, its value is 1. At irrational points, its value is minus 1. Each in is irrational. Therefore, f of in equal to minus 1 for every n. A is a rational point. Therefore, f of A equal to 1. Right? Therefore, what is limit f of in? Then what is limit f of in? Because first term f of I1 is minus 1. F of I2 minus 1, f of I3 minus 1, f of I4 minus 1. Therefore, this is a constant term. Therefore, limit f of in equal to minus 1. Limit f of in equal to minus 1. Right? Because f of I1 equal to minus 1, f of I2 equal to minus 1, f of I3 equal to minus 1, and so and so. Therefore, this is only a constant sequence. Therefore, its limit is nothing but minus 1. What is f of A? A is a rational point. Therefore, by the definition of f of A must be 1. Now, here we have in converges to A and f is continuous at A. Therefore, we can take f on both sides because by this sequential criteria of continuity, in converges to A. Therefore, f of in converges to f of a, since f is continuous at x equal to a. Therefore, f of n equal to f of a. Therefore, that is, what is f of n converges to f of a means? Limit f of n equal to f of a. But we already mentioned that what is limit f of n? Minus 1. What is f of a? 1. Therefore, minus 1 equal to 1. It is a contradiction. Therefore, this is the assumption is f is continuous at x equal to a, where a is a rational point. That is not true. Therefore, f is definitely discontinuous at all rational points. Simply, here we have 1 equal to minus 1. Sorry, minus 1 equal to 1. This is the contradiction. Minus 1 equal to 1. This is the contradiction. Similarly, we can discuss the case of irrational case. You take a irrational number a, then we can we can construct a sequence of rational Rn converges to a. Then limit f of Rn equal to f of a. Then we limit f of Rn must be 1 and f of a equal to minus 1. Then we will have another contradiction. 1 equal to minus 1 instead of minus 1 equal to 1. Here we have the contradiction, minus 1 equal to 1, but in the next case, the contradiction will be 1 equal to minus 1. Therefore, f is discontinuous at all rational points. Similarly, we can prove that f is discontinuous at all irrational points. Therefore, the consequence is this function is everywhere discontinuous on R. Right? This function is everywhere discontinuous on R. Now, I think the proof is easy for you. And now you just try to answer this question. Find infinitely many such examples within 5 seconds. This is I think now this is not a challenge for you. Now this is a very easy question. Because 1 minus 1. The case is 1 equal to minus 1 is possible? Never. 1 cannot be minus 1. If 2, 3, 2 not equal to 3. Therefore, that is example. Here, if f of x equal to x, if x is rational, and minus 1 if x is rational, then x equal to minus 1. There is one possibility. So, I think now we have infinitely many everywhere discontinuous function. For example, you take f of x equal to x plus 1. If x is rational, x minus 1 if x is rational. What is that? Instead of 1 and minus 1, I am using x plus 1 and x minus 1. Then question is whether x plus 1 equal to x minus 1. Then x get cancelled and there remains again 1 and minus 1, but 1 not equal to minus 1. Okay, therefore, the second example is what is that? F of x equal to x plus 1 if x is rational and x minus 1 if x is irrational. Then the question is whether x plus 1 equal to x minus 1. No. If equate, x get cancelled and there remains again 1 equal to minus 1. So, I think now we are in a position to give infinitely many counter examples for the very first question. Okay, right. So I always concentrating on this question. Find infinitely many such examples within 5 seconds. If you take 1 minute, I think that's not a good one. We have to answer it within 5 seconds. That is very important. The next one, now you just think about the next question in the first slide in our storyboard. The question was about this one. Construction of a function f which is continuous at exactly 1 point. Here the moving is like this one. The function goes to 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1. There is a kind of oscillation. And there is a kind of oscillation. There is a kind of significant oscillation. All right. Here, what are they? X. This is the graph of y equal to x. This is the graph of y equal to minus x. So, the first when at a rational point, the function goes to x. At any rational point, it goes to minus x. oscillation, no oscillation, but the distance between these oscillation that will reduce us to almost zero as we approach us to zero. Of course, we admit that the here also we have the oscillation, but the distance between the oscillation that will tends to zero as we when tends to zero. So this is the function x equal to so again this is the way x, if x is rational, or f of x equal if x is rational, and minus x if x is irrational. We know that rationals are dense in R, irrationals is dense in R, their intersection is empty. So x have a irrational path as well as an rational path. Okay, towards zero. So the question is, at what point this function is continuous? The question is, you just think about x equal to minus x, then 2x equal to 0. X equal to 0 is the only possibility. These steps are not hard. We can independently, from the classical sequential criteria, sequential form of density theorem, we can show that x equal to 0 is the only possibility. So we can neglect all the other possibility. The only possibility is x equal to 0, because here x minus x, you just put x equal to minus x. Okay, then that is only possibility x equal to 0. So we can naturally neglect all the other cases. Now look at this. This is the graph y equal to x. This is the graph of y equal to minus x. So what is the graph? What is the shape of the graph above the x-axis? The part of the graph above the x-axis is nothing but mod x, right? The part of the graph above the x-axis is nothing but mod x. While, yes, okay. Similarly, the part below the x-axis is nothing but minus mod x. So the function, it takes it either it is x or it is mod x. The graph is above the x-axis is the graph of the mod x, and below the x-axis is nothing but the graph of minus mod x. From the figure, it is clear that f of x is never above mod x, nor never below minus mod x, right? I am repeating, f of x is never above mod x or never below mod x. That is, f of x always lies between minus mod x and mod x. Therefore, f of x is a sandwich of minus mod x and mod x. Now look at this one. Limit extending to 0 minus mod x. You just substitute 0 here. Minus mod 0, 0. What is limit tends to 0 mod x? That is again 0. Therefore, as a sandwich, limit extending to 0 f of x, that must be 0. What is f of 0? 0 is a rational number. Therefore, f of x equal x, f of 0 equal 0. Therefore, f of 0 is 0. And limit extending to 0, and the limit extending to 0, f of x is 0. Therefore, the limiting value and the functional value at 0 is the same. Therefore, definitely f is continuous at x equal to 0. We already said that x is equal to 0 is the only possibility. Now we conclude that f is continuous at x equal to 0. Therefore, f is continuous at exactly 1 point. So we answered the second question also. So again, my question is, give such infinitely many examples within 5 seconds. Okay. Okay, so we another we can easily we can tell about another example, x plus 1 if x is rational, minus x plus 1 if x is irrational, something like that. I think now we are in a position to answer. We have infinitely many choices for answering this question. Okay, so we are moving to the next one. Before going to this one, I am just trying to calculate f dash 0 is here. Therefore, all other points are discontinuous points. Therefore, no possibility for differentiability at all at that points. So, only possible point for differentiability is x equal to 0. So we just try to calculate f dash 0. What is f dash 0? Limit extending to 0. Fx minus f0 divided by x minus 0. What is f0? 0. What is fx? Either x or minus x, or either x by x or minus x by x. But x by x is 1 if x not equal to 0. Therefore, either 1 if x rational or minus 1 if x is irrational. This is our this is our previous question. This is nothing but our previous question. Either 1 or minus 1. The limit of this one, the limit of this function, that does not exist by last theorem. Therefore, this limit does not exist. This limit does not exist. Therefore, f dash 0 is x. Therefore, this function is everywhere non-differentiable, but continuous at exactly one point. This is the idea. Okay. Yes. So I am again inviting all the students to answer this question. Find infinitely many such examples within 5 seconds at the most. Okay. I think now you got the idea to generate such examples. Now we are moving to the third question. Construction of a function f from R to R, which is differentiable at exactly one point. Again, the technique is rational path, irrational path. Otherwise, that will not work. If x is rational, it is x square. X is not sufficient. So the first example is 1 minus 1. Then we multiply 1 minus 1 by x. Then we will get a x and a minus x. Now we multiply that x minus x by x. Then x square and minus x square. That is f of x equal x square if x is rational and minus x square if x is irrational. So what is the possibility for continuity? We know that the quick observation. What is that? You just put x square equal minus x square. Then that is 2x square equal 0. That is x equal 0 is the only possibility for continuity. So we can neglect all the other possibility. Only possible point for continuity is what is that? X square. Then what is the graph of this one? What is the graph of this one? This is for parabola x square. Y equal x square. This is the parabola y equal minus x square. Therefore, either x square or minus x square. Again oscillating, but the distance between the oscillation that will rapidly decreases to 0. All right. So, as an above, the function, the graph of f of x is never above x square or nor below minus x square. So, as in the previous case, we will have this function f of x lies between the minus x square and x square. Look at this graph. F of x, either this one or this one, either this one or this one. Therefore, the graph never above x square nor below minus x square. Therefore, f of x is a sandwich of minus x square and x square. Right? Then what is limit extending to 0 minus x square? This is simply 0. What is limit extending to 0 x square? That is again 0. Therefore, that sandwich must also converges to 0. That is limit extending to 0 f of x equal to 0. Therefore, the limit extending to 0 f of x equal to 0. Now we have to find out 0. 0 is a rational number. When is a rational number f of x equal x square? Therefore, f of 0 equals 0 square. It is simply 0. Therefore, f of 0, 0. Limit is 0. functional value equal to the limit. Therefore, by definition, by the very simple definition of continuity, f is continuous at x equal to 0. In fact, f is continuous only at x equal to 0, right? F is continuous only at x equal to 0. Therefore, only possible point for differentiability is x equal to 0. In the previous case, it is not differentiable at x equal to 0. Now we are trying to find out. We can neglect all the other cases. Now we are trying to find out f dash 0. What is f dash 0? Again, limit extending to 0, fx minus f0 divided by x minus 0. We already calculated f0, that is nothing but 0. Therefore, f of x by x. What is f of x? Either it is x square or minus x square. Therefore, x square by x, that is on simplification, that is x. Or x square by minus x square by x, that is minus x. Therefore, f dash 0 equal to either x or minus x. But if we put 0 on here, it is simply 0. Minus 0, that is again 0. 0, again 0. Therefore, f dash 0 is 0. This is the nothing but the very last problem. Okay, x minus x. This is the last problem. Okay, that is what is f dash 0? 0. Therefore, the derivative exists at x equal to 0. F is different. Therefore, f is differentiable at x equal to 0. In fact, f is differentiable only at x equal to 0 because f is continuous. Since f is continuous only at x equal to 0. Okay, we already mentioned that f is continuous at x equal to 0. What is that? In fact, f is continuous only at x equal to 0. Therefore, only possible point for differentiability is x equal to 0. And at that point, f is differentiable. Therefore, this function is differentiable only at exactly one point. Is differentiable at exactly one point. So naturally, my next question is find infinitely many such examples within 5 seconds. Definitely, of course, the very simple or trivial solution, what is that? You just f of x equal x square plus 1 if x is rational, minus x square plus 1 if x is rational. Then there is no effect for the adding 1. There is because when we put x square plus 1 equal minus x square plus 1, that 1 get cancelled, and it is equivalent to the just the former case. So that is nothing new, independent solution. So you just think about the independent solutions. My question is, I am asking for infinitely many such examples. But the very important thing is you have to answer that all such questions within 5 seconds at the most. So we discussed the continuity, differentiability. So one more, integrability. I think I am not proving to anything about this criteria. You just assume this condition. Lebesgue integrability criterion. A bounded function f from a, b to r is Riemann integrable if and only if it is continuous almost everywhere on a, b. Okay, that is measure of non. You just leave the technical details of that theorem. If it is that is a Riemann integrable function has a bounded Riemann integrable function has at most countable number of discontinuity and conversely. That is the actual version. If we have only one point of discontinuity, then it is a Riemann integrable. If a function has discontinuous at 2 points, then it is a Riemann integrable. At the most, if it has countable, even if it has countable number of discontinuity, then also it is Riemann integrable because it is an if and only if result. Therefore, we can use it as a definition. So I am directly asking this question to you. The question is this one. On closed interval 0, 1, which of the followings are Riemann integrable? I think the first option is you are very familiar with. This is the famous Dirichlet unit function. The second question is f of x equal to x minus x if x is rational, minus x is if x is irrational, x square minus x square. X square minus x square. Okay. So I think the previous discussions are enough to attack option B. Okay, this is C. Option B and option C. Okay, right? So, thank you. I am stopping here, and you can ask the doubts now.
If
Thank
you
you,
have
sir.
any doubts, please ask right now. Anyone? So thank you, sir. So next I will invite Ms. Shani Varghese to deliver the vote of thanks.
Good evening all. It's a great honor for me to propose a vote of thanks in the national webinar conducted by our college. I extend a very heartfelt thanks to our chief guest, Sir Albert Antony, for joining with us and for giving a wonderful session on application of density theorem. We could get to know more about two different examples. It was very helpful for understand and interesting. I believe that it will definitely help us to future studies. Thank you, sir, for spending your valuable time with us. And I thank everyone who joined with us in this session for making this a successful one. Thank you.
Thank you, Shani. A few attention to the participants. Any certificate of participation shall be shared after the feedback form is filled. Link for the quiz and the feedback form will be shared in the chat box. Thank you all.
Thank you, sir. Thank you so much.
Okay, thank you.
പറ ഇതിനകത്തോട്ടില്ല